We're at Hoover High School AP Chemistry. This is Unit 6, Kinetics Rate Law. So we're going to talk about probably one of the most significant things you're going to learn in this unit is about the rate law. So what is it? So the rate law is simply an equation that incorporates the concentrations of the reactants, and using the rate constant will give you the rate at an exact moment in time, how fast that reaction, how fast those reactants are going down in concentration, because reactants go down in concentration. So let's learn how we do this. Let's take this example. Nitric oxide gas, NO, reacts with chlorine gas according to this equation, and the following initial rates of reaction have been measured for a given reagent of concentrations. So let's take a look at what this is saying. You ran three reactions in a lab, and in the first one you used a concentration of NO of 0.25 molar and 1.5 molar of chlorine. And you found that the reaction at a specific moment in time when those concentrations were present, the rate was 1.19 molar per hour. In other words, the concentrations of the reactants are decreasing by 1.19 molar, that's moles per liter, for every hour that goes by. That's the speed of the reaction. Now you ran it a second time with different concentrations, 0.5 molar of NO and 1.5 molar of Cl. And you found that the rate under those concentrations was 4.79 molar per hour. That's the speed of the reaction. Finally, you did it with 0.5 molar of nitric oxide and 3 molar of chlorine gas, and you found that the rate was 9.59 molar. So using that data, you can derive an equation that will allow you to put in any concentration of NO and Cl2 and determine how fast the reaction will run with those concentrations. So create a rate law of the form, and this is the general form of the rate law. Its rate law, or rate, the rate of the reaction will equal the rate constant K times the first reactant, which in this case is NO, and raised to some power X, and then the concentration of chlorine gas, Cl, raised to some power Y. So what we have to figure out to develop this equation is what is the value of K, what is the value of X, and what is the value of Y. Note that the coefficients in front of the reactant, such as 1/2 in front of the Cl2, play no part in the process. They have nothing to do with it. Alright, so first find the value of X, the exponent for NO, by isolating a change in concentration of NO and the change in the rate that it produces. So find two reactions where NO changes and Cl is held constant. So you're just trying to look at what effect NO has on the rate. So you want Cl to be constant. So reactions 1 and 2 meet that criteria. In reactions 1 and 2, Cl is 1.5 molar in both of those, so it doesn't change. But the NO, you can see in reaction 1 is 0.25 and in reaction 2 is 0.5, so that's different. So you're going to see how the different concentrations of NO will affect the rate, how fast the reaction takes place. So we're going to pick those two reactions. So you create a ratio of the concentrations of NO. So you have 0.25 and 0.5. You can put them in either order, you can put either one on top, but it's wiser to choose to put the bigger one on top so you don't end up with a fraction. So 0.5 over 0.25 equals 2. So you've doubled the concentration of NO. How does that affect the rate of the reaction? So you create a ratio of the rates of NO, the rates with those two different concentrations of NO. Now, since you put number 2 on top of number 1, that was the 0.5 over the 0.25, you have to do it in the same order for the rate. So you have to put the 4.79 over the 1.19. And so you do that ratio for the rates. And that gives you about 4. So what you're going to do now is you're going to figure out what power do you need to raise to the number 2 to in order to get 4. So let's go ahead. So since the ratio of equation 2 over equation 1 was equation 2 over equation 1 in the first ratio, it must be equation 2 over equation 1 in the second. So again, what I was saying, that you put equation 2 over equation 1 in both of those. All right. So here's what happens. You now equate the concentrations rates with the exponent x. So here's what you do. You take that 2 and you place it down there, and then you place the 4 on the other side of the equal sign, and you put an exponent above the 2 to the x power. So you put the exponent on the ratio of the concentrations, not the ratio of the rates. You put it above the 2, not above the 4. Don't make that mistake. So you simply have to ask yourself, what power do you raise 2 to in order to get 4? And the answer would be 2. 2 to the second power would give you 4. So what that means is that 2 is the exponent for NO. That's the x value that exponent for that's the exponent for NO that we're looking for. So that's the reaction is second order in NO. Now we're going to do the same thing to figure out what the y value is, the y exponent for Cl2. So we need to find two reactions where NO is held constant. And that would be reactions number 2 and 3. You see that it stays at 0.5 in both of those reactions. So what we want to do is analyze what the change in Cl, what effect that has, the change in Cl2 to the rate. So we do the same thing we did before. We're going to go ahead and put 3 over 1.5 since that gives us a whole number. It doesn't give us a fraction. So we decided to put, in other words, reaction 3 over reaction 2. So you have to do the same for the rate. So that means you're going to put 9.59 over 4.79, and that gives you approximately 2. It doesn't have to be exact, it just has to be approximately 2. So we're going to go ahead and set up the exponent the way we did for the last one. We chose to put reaction 3 over reaction 2. Okay, so here we go. So we take the 2 from the concentrations and we put it down there. We take the 2 from the ratio of the rates and we put it over on the other side of the equal sign. And then we put the exponent up above the ratio, the 2 that represents the ratio of the concentrations. So 2 to the y power equals 2, and of course that's 1. Y equals 1. So there you put that right there above as the exponent of Cl2. So now you've figured out both of the exponents. Now the final step is to figure out what the value of K is, and how do we do that? Well, we pick any reaction. We can pick any of the 3 reactions, and we plug in the numbers. If you look at the equation up above, that's the equation we have so far, NO to the second power and Cl to the first power. We know the concentration of NO. We know the concentration of Cl for this reaction. We're using reaction number 1. And we know the rate for that reaction. It's 1.19. So NO is 0.25, Cl is 1.5, and the rate is 1.19. So we can plug those numbers into that equation up above. The only unknown we will have in that equation is K. So when you do that, down below right there where the yellow arrow is pointing, 1.19 equals K times 0.25 squared times 1.5. And when you solve for K, over there on the right, you end up with 12.7, and it's 1 over molar squared per hour. Okay, we'll talk about how we got that number. So that's the value of K. So the rate of the equation is 12.7 NO squared Cl2. What does that mean? And how can you check your work, by the way? It means that whatever concentration of NO you put in and Cl you put in, and you run it through that equation and multiply by 12.7, the rate constant, it will give you the rate. So let's take equation 3. If we took the value of NO in equation 3, that's 0.5, and put it in where NO is, take the value of 3 for Cl2 and put it where Cl2 is, and then run the math on that and multiply by 12.7, the rate constant, it will give us the rate that we see over here for equation 3, which is 9.59. That would be the answer you would come out with. So it tells you for any 2 concentrations of NO and Cl, given that rate constant, you will get a certain rate. It'll tell you how fast that reaction will be taking place at that time. K is dependent on temperature. So if temperature goes up, that will cause K to go up. So for this equation to be valid, you can't change the temperature. It has to be at whatever temperature you did this reaction. You can't change it. At a different temperature, K would be at a different value. Generally, the higher the temperature goes, the higher K goes. That is, the faster the reaction will take place. So there's your final answer. Okay, so what are the units of measure? We actually saw them back there on the previous slide, but how do you figure them out? Because they're not the same. It depends what the order of the reaction is to determine what the units of measure are for K. So the answer will depend on the order of the reaction. This reaction, the rate is 12.7 times concentration of NO squared times concentration of Cl2. So you can calculate the units for K by the fact that the units for rate are molar per hour. It's how many moles per liter are changing per hour. So that's a rate, that's a speed of the reaction. Meaning that how fast does the molarity change per hour? Different problems use different measures of time, such as seconds or minutes. So here's how you would write that equation up above in units of measure. On the left-hand side, you have rate, that's measured in molar per hour, equals question mark. That's what we're trying to find out. What are the units of measure for K, the rate constant? So what you have in NO squared, the concentrations, NO and Cl2, are measured in molar. So since NO is squared, you have to square its unit of measure. So molar gets squared down below. And Cl2 is just raised to the first power, so you just have m there. So you have m squared times m, that's going to give you m to the third. So what we do is divide through by m squared and times m. And the NO and the Cl2 are molar concentrations. The NO is squared. So there it is, the same equation. So we just get down there. We divide both sides by m squared and m. And so what you have over on the, I switched the sides of the K, but what you have is m per hour, that's the rate, over m squared m. And you can see that one of those m's on the bottom is going to cancel. Right there, m and m. So you have 1 over m squared hours. And that's going to be your units of measure. So you can see that the unit of measure is going to depend on whether it's a first order, second order, third order equation. That's going to determine what the units of measure for K are. The final answer with units of measure for K is, there it is, 12.7, 1 over molar squared hours times the concentration of NO, or that should be to the second power, times concentration of Cl. Okay, let's talk a little bit about logs and natural logs. We actually talked about logs and natural logs back in lesson 2. That was a long time ago. So let's just do a quick review of that. So logarithms serve two purposes. They make it possible to plot a wide range of exponential values on a piece of paper. So if you plotted y equals 10 to the x, if x equals 0, then y will equal 1. If x equals 6, then y will equal 1 million. You can't plot a range of values from 1 to 1 million on a piece of graph paper. So what a log does is it allows you to be able to have a range of values that is more reasonable to be able to be plotted. And it linearizes, makes a straight line of exponential curved functions. So let's go back and review what we saw, what we learned back in Unit 2. I think that would be helpful to understand this. Alright, so here's a slide that we saw back in Unit 2. So logarithms serve two main functions, which we just mentioned. They linearize, make a straight line out of a curved exponential function, and they scale down outputs of an exponential function to make graphing possible. So here you have a graph of y equals 10 to the x. That's an exponential function. That means it has a variable in the exponent. That's called an exponential. So you can see if you go from values of x0 up to x equals 5, you can see how big the range of y values is. They range all the way from 1 up to 100,000. You can't possibly graph that on a piece of graph paper. If, however, you decided to graph y equals log of 10x, then what you do is that same domain, 0 to 5, you have a very limited range of outputs of y. It just goes from 0 to 5. So that's something that you can very easily graph on a piece of graph paper. So here's a graph of y equals 10 to the x. If we plot an exponential, the graph will increase so quickly that it will not fit on a piece of graph paper. It also produces a curved line. And it's hard to analyze curved lines. You need calculus to do that. So if you extended that graph, by the way, the size that it is on my computer screen at least, to x equals 10, that red line would reach beyond the moon. That's how fast it would go up. Now here's the graph of y equals log of 10 to the x power. Plotting x against the log produces numbers that can easily fit on a piece of graph paper. It also linearizes, so it creates a straight line out of the data. So unlike the graph on the left, this graph can easily display x equals 10. So that's what logs do for you. For our purposes in studying kinetics, the range of the values is not that significant. Its ability to scale down the range of the values. What's significant is its ability to create a straight line. Okay, so logs can also create straight lines from exponential graphs. This is the reason natural logs are used in chemical kinetics. Exponential functions have a variable in the exponent, so y equals 10 to the x, what we just talked about, or y equals e to the x. In this unit, you will learn to use the natural log function ln of x to create straight line graphs out of reaction rate curves. All ln is it's log log to the base e, which is 2.718. So it's just a base that appears in nature quite a bit. That letter e represents 2.718. A natural log is a log to the base e power. So log base e x equals natural log of x. So we don't ever write log base e, we just write natural log ln. You don't need to have an in-depth understanding of ln or e, believe me, you don't. You just need to know enough to when to apply it in kinetics. It's basically when to plug the numbers into it. This is not a course in natural logs, but you need to understand the idea of inverse operations for natural logs. So an inverse operation, math operation, reverses another math operation. Example, addition is an inverse of subtraction. So y plus 2, and then subtract 2, you get back to y again. So addition and subtraction are inverse operations of each other. In math, there's a special number called Euler's number, and that's E, and that's E equals 2.718. This number describes changes that appear in nature, such as chemical reactions, and a lot of other things as well. You will use the following inverse operation between E and natural log. So ln x is the inverse of E raised to the x. And there's the property of logs that we saw back there, so you could refer to this as needed. This was back in lesson 2 as well. So you will use the following inverse function. Ln x is the inverse of e to the x. So take any number y, ln e to the y equals y. So in other words, if you got the y up there in the exponent of e, you just take the natural log of e and it will get you back. It'll kind of unwrap that y and get it out of there. Similarly, if you have ln of y, you simply raise e to the ln of y and it will return y. So they reverse each other. In both cases, you begin with y and you end up with y because e to the y and ln y reverse each other. Another principle of logs you should be familiar with is the following, that log of a times b equals log of a plus log of b, and log of a divided by b is equal to log of a minus log of b. That will come up in some of the problems we do later on in this unit. All right, so that takes care of this. This was really the problems 17 and 18 on the day 51 assignment are based on the first part of this lesson. So go ahead and review that. Now what you should do is not just view that problem, and I'm talking about the rate law problem. Write it out. Actually write it out in your notebook and write it out on scratch paper several times until you can do it from memory. You don't have to memorize the table that we use. Just have that to view. But you should be able to know how to do the steps from memory. Okay, that's when you know that you really can do a problem, not just watching it on a video, okay? So we'll be back with the next lesson tomorrow, and we're going to get through this unit this week. Have a good evening.